This topic will be presented by Branko, who is a hybrid cloud and AI technical manager with over 12 at IBM. His topic is Neuro-Symbolic AI, an emerging class of AI workloads and their characterization. And the Neuro-Symbolic AI initiative aims to conceive a fundamentally new methodology for AI and address the gaps remaining between today's state of the art and the full goals of AI, including artificial general intelligence. So now, without further ado, I give word over to Branko to present his talk.
Hi, thanks, Ognjen. That was quite an elaborate introduction. Can you confirm if you can hear me well?
I can confirm I can hear you well. Hear you and see you. Everything is okay.
Good. Okay. So hi everyone. From me, I'll jump straight to the content of the presentation. While I'm sharing my screen, I'll just some of you already know me from previous years. So basically, I run IBM's technical team for Eastern Europe. Among that, people who deal with the data and AI. And as a part of my job, I follow or I kind of study the advances that are made in various IBM research centers around the world in this area in order to know what comes next, what's the next step for our customers, for our partners, where do we invest in the skills and so on. So today I'll be talking to you about the Neuro-Symbolic AI. And this content of today's presentation is based on research made in the joint MIT-IBM Watson AI lab. The lab exists for almost 2 years now. They already have now over 60 running projects. So this slide is not up to date, but there's a significant investment from both sides, and there's a lot of researchers, over 150 researchers, PhDs, and their associates who are working on various types of AI projects. I'll be focusing today on the Neuro-Symbolic AI because this is something that is, I would say, a re-emerging technology, something that is a revamp of the old math that we used to have in the 50s and the 60s. But I encourage you all to visit the link that you can see at the bottom of this page. And there's a whole mini portal with all the projects of the MIT IBM Watson AI Lab in different areas and links to all the research papers, demos, code, materials, and so on and so on. So to jump straight to the point, I guess you're all aware of the kind of this ladder of evolution of AI, how we started with addressing some tiny individual niche problems or point problems where today's AI is very good, like recognizing faces, like recognizing things on the photograph, like predicting whether you should receive a loan or not. So these are like really well-defined narrow problems that AI can tackle very well. The next step is obviously broad AI, when basically the data that we serve to the AI is, I would say, more complex or more diverse, where we expect the AI not only to report one number or one decision or whatever, but we expect the AI to look at the problem in a kind of multi-domain or multitask mode and to see the problem from various angles. And something that awaits us in the distant future, which, according to some authors and well-known people, is when the robots will come and kill us all, is the general AI, where we get to the point that AI is nearly self-conscious or self-aware, meaning that it's pretty autonomous in performing certain things. So looking at this, we are on a journey, and this journey is kind of going from left to right, going from simple, narrow AI problems and the tools to solve these problems to very, very complex problems that can be solved by even more complex AI of the future. And in order to reach those tools, the researchers of MIT and IBM have defined some general points, or this is basically the industry consensus that in order to reach the higher levels of AI, or to reach the higher level of complexity of the problems that can be resolved with the AI, we need to take care about several important factors. One of them is the explainability, obviously knowing how a specific black box model has reached some decision or recommendation or prediction. Then, of course, the security, the ethical part, Then, how do we tackle with problems that, in the industries where we do not have huge amounts of data, which is a big problem for today's AI, because today we know that the AI is as accurate as, the data that's coming in, and we typically expect loads of data in order to properly train the model. And obviously, this is all related with the development of the infrastructure, and you've seen in this DSC and in some previous years, a lot of material around quantum computing and some different ways in which hardware manufacturers are tackling this problem and trying to kind of come up with the hardware that will be good enough for us to move toward that a broad AI or general AI. And obviously, below all that, we need to have tools to manage the data. We need to kind of cleanse the data. We need to have the methodology, we need to have the compute power and so on, which is the basis of the whole thing. And looking at this from different perspective, right now we are dealing with the AI which is emerging, meaning that it's solving particular problems. It's quite under our control still. And currently our AI is, I would say, fitting into the life as we know it. So currently most AI models are somehow augmenting or replacing something that the human would do. They do similar things that the humans would do, but they do it faster, they do it more accurately, and so on. The next step where we are, as you can see at the bottom, where we have only stepped in, is this broad AI. And the characteristics of the broad AI is that it tends to be disruptive and pervasive. What does it mean? It means that broad AI will change our lives. Will introduce significant changes. For instance, self-driving cars will significantly change our lives, because obviously in the future this means that people will not either be able or people will not be taught to drive. There will only be AI drivers. And on the other hand, it will be pervasive, meaning that the AI solutions, once adopted, they will prevail over the traditional, I would say, human-centric solutions. So again, once the self-driving cars become standard, then it will be very difficult as a human to drive in that self-driving world, because then you will be the only guy who is making the mistakes, or the guy who is making the most mistakes. And this is why these technologies will, in fact, change our lives significantly. And obviously, the third step is something that will happen according to futurologists, in the years 2050 and beyond, is something that will become revolutionary. And here we are talking about something that will basically, be similar to human mind in terms of capabilities, but work in a probably completely different way. So, what's so narrow about what we have as AI tools today? Why do we have an issue? Why are we not further down this development path and all the way to the right even today? When we look at the technology and the math that lies behind AI today, and if we use image recognition as an example of a classical traditional problem where AI algorithms are heavily used and they have performed very well, we know that the math that lies behind this, and this is typically neural networks, CNNs, and so on, this math has been devised in the 50s and the 60s of the previous century. So we had the math at that point, but what was lacking is obviously the computing power to be able to simulate, to train the models and do it in real lifetime of the scientists who were dealing with this problem. And we were also lacking, I would say, the possibility to generate big enough samples of data to train the models properly. And ImageNet is obviously one of the great examples, because once this data set was developed, it opened a whole new world for the data scientists to create a very, let's say, high performing set of models. And here you can see that where we are today, based on the neural networks and the ImageNet the demo library. You can see that based on different algorithms that we can achieve the so-called superhuman performance, meaning that even today we have AI algorithms based on neural networks that are able to recognize images or objects in images better than the humans. And this is something that is a huge success, obviously, and we've come a long way when it comes to this particular type of problem. And some of the examples of the things that are possible today with these algorithms is, you can see these are automatically generated captions by the machine learning model. So a man in a black shirt playing a guitar, and then a construction worker in orange safety vest is working on the road. So perfectly described. This is like a perfect score for the AI model. However, when we introduce some examples which are less similar to the training data from ImageNet, and these are typically the examples where the objects in the picture are not in some, I would say, a logical order, or they are not logically combined or merged, problems will happen. So if you look at the picture on the left, first of all, monkey is recognized as a person. And obviously, the reason why the monkey is recognized as a person is that there are some surprising things on the picture. On the left, you have a bicycle. On the right, you have a guitar. So since the system was not trained in any remote combination of monkey and the bicycle, probably, and the monkey and the guitar, then according to the AI model, this must be a person. And also, you can see that that in both of these pictures, the steering wheel of the bike and then the guitar were identified as a bird. And obviously, the reason for that is that in the jungle setting, the training data set that was used for this model was obviously, when there is a jungle, and there are some flashy colors or some weird shape, then probably it's a bird. And this is where these models kind of do not provide such a good information. Some other or further examples of this is that, for instance, a man riding a motorcycle on the beach, and this is a categorization of a scene of a World War II war scene. Then, an airplane parked on the tarmac, and then the group of people standing on top of a beach. And then when you look at these pictures and you imagine some automated AI-based newscaster, which is maybe looking at some videos from public surveillance cameras and trying to find some news, you can imagine that in this picture on the right, this newscaster would say, "Oh, we have some people standing on a beach, so obviously, everything is cool and nice, and you should go to the beach." That would be the conclusion if you were not able to see the picture, if you had an AI-based newscaster. So this can lead to obviously serious problems, and this is not something that we are looking at in terms of developing our complexity and the accuracy of the AI that we have. And one more example is obviously this piece of art where a human can immediately see that this is a coffee cup with a coffee spoon. It is made from fur. It's a piece of art. However, when you show this to the AI model, it will categorize this as a teddy bear simply because it's round, it's fluffy. So all the things that AI model has seen in the training data that is round and fluffy, most likely it will be a teddy bear. So another example that shows even a little bit more on how serious or how dangerous these deficiencies can be. This is an example from the MIT IBM lab where they have a simulated security system that is looking at the camera feeds and detecting basically the people, if there are people or intruders in the picture. And as you can see on the right, the person wearing black clothes is properly identified. However, on the left, the person is not identified or by the AI model. And the reason for that is that he's wearing a specially designed shirt. And this shirt actually, while this picture looks at the fruit, it's actually some abstract picture, but it was purposefully designed to hack this security system, to trick the AI model into thinking that this is not a person. And obviously this succeeded in this example. So they were able to create a very simple thing as a printed T-shirt, and this fooled one of the kind of most precise AI models in terms of recognizing something as a person. So here you can see that there are even more serious potential consequences of having such a deficient model. Another example is, if we look at this, and I'm not sure if people can kind of jump in or provide comments, but If you were guessing what this is, probably not many of you know what it is. It looks like some kind of antenna, but I will tell you, details in the next couple of seconds. Maybe people who are, let's say, slightly older generation like me remember something that was advertised as the Swedish TV detector. So when, like, maybe 30 years ago, the employees of Belgrade TV were walking around the city with these things, and they were trying to detect who is watching TV without paying subscription. So this is basically the antenna used to hunt people who are, cheating and not paying their TV subscription. However, as humans, we are able to look at this and to learn this information, to recognize this just based on one, so literally one image. And then if we look at the next image, yes, we can recognize that the same thing is appearing on this picture. Is it present? Yes, we can easily answer that question. How many of these are present in the picture? There are two. So again, extremely easy answer for a person, extremely difficult for an AI model with only one example to learn from. And then imagine giving AI this picture. Immediately you can see that we have the same thing even in this picture, although it's a bit weird, you have to admit. But there will be absolutely no chance that an AI model would be able to say that this is a TV frequency detector. They would say it's some sort of a man with a weapon, most likely. And then when we look at the results that neural networks are giving based on the images, in the ideal cases, as I said, they are ranging over 90%, even going to 95 to 98%. However, these are all based on the very clean staged images that you can see as part of the ImageNet library. What MIT IBM researchers have done is they have enlisted a lot of, let's say, a group of volunteers, and they asked volunteers to send them pictures where these same objects, like the chair, are not in such a perfect position to the camera. They are not staged for the camera. They may be in some awkward positions or pictures taken from awkward angles, or maybe there are some unusual objects found on the chair, like this bottle of shampoo. And once you have examples like this, the accuracy of your model drops by 40 to 45%. It drops by half, literally. So basically, you come from something which is, a very much production-ready model, which has, like 95+% recognition. You come to something that is, not really production capable, because it gives you the accuracy of, let's say, 50% or less. So depending on the example, if something doesn't, if something is not staged as logically as it is in the ImageNet library, then the results drop significantly. And similarly, if you try to use the same model to answer some of the very simple questions, like how many blocks are on the right of the 3-level tower, or are there more trees than animals in the picture, or what is the shape of the object next to the large cylinder? For humans, this is extremely easy to answer. And then for the AI models, even the most perfect ones, based on the neural networks that are doing perfect image recognition, they are not able to answer these questions. And we have to compensate for this by writing some software with business logic that is then able to count, subtract, query the model several times, and then come up with the answer. So this is where the symbolic part comes in. At approximately the same time when neural networks were developed, generally the science and the math came up also with the concept of symbolic reasoning. And unlike neural networks that basically look at the apple as a series of pixels, and then they look at take this picture through different filters, and then they do kind of recognition on different patterns. The symbolic AI works in a different way. The symbolic AI describes some object using a set of concepts, like the origin, the structure, and the kind, and then it creates a set of relationships that can give us different aspects of information about this specific item. For instance, we know that apple comes from an apple tree, so we know its origin. We know that in its structure it has a body and a stem, and that the body can be red or green. We know that the apple is a kind of fruit, and so on and so on. So back in the 50s and 60s, this became the fundament of something that we used to call expert systems. And if you remember, again, a slightly older generation will remember that in the 80s, expert systems were quite popular, and all the software developers were trying to implement expert systems or use these principles in their design, and basically implement kind of these systems, IT systems, which have unlimited or extendable database model, or sorry, data model or data schema, so that you are not limited to a specific set of properties or specific set of relationships. But over the years, since this approach was kind of much easier to simulate using relational databases and a finite number of parameters, this approach was pretty much abandoned, and it's no longer used. However, now it's coming back as a potential, I would say, enrichment of the neural network based model. And basically what I will take you through now is a kind of mind experiment. If we try to use the neural networks to answer a simple question, what is the shape of the red object? What the neural network would do is, obviously, it would find the concepts, or find the what are the colors, what are the shapes, what are the properties on this picture. It would be able to do some reasoning, so it will be able to count the number of specific items. But these information would be entangled, so it would be able to count that there is one green cube in this picture, but then if you had another picture that has a green I don't know, sphere, then it would be a completely new set of learning. So the problem with this is it's very difficult to generalize, to use a set of training images and then to have the AI have a generic coverage or to answer more general questions. And this makes it very difficult. You need to prepare loads and loads and millions of training examples. And now, if you look at how human brain is doing a task like this, so look at the picture, and the question is, are there an equal number of large things and metal spheres? Obviously, as humans, we would say, yeah, there are 3 large things. Yes, there are 3 metal spheres, and the number is equal. So for us, we use logic in this process to kind of cover this question. So there are several components of this. If you looked at neural networks and how would you implement this, obviously you would use filters to determine the size, color, and the number of objects, and you would create some sort of table or a matrix with this information. Then you would use a separate algorithm like LSTM to basically parse the question to find out what the author of the question wants to find out. And then you would create like a simple program and run this program or a set of filters or operations against this data set or a table, and then you would come up with the answer. So in this case, you would need kind of 2 different algorithms for vision and language, and then you would need to kind of create structured representation of what was found using the vision algorithm, and then again you would need to write some form of program to solve this issue. And now let's see how it works in the world of the Neuro-Symbolic AI through a kind of simple hello world example. Imagine again that we have this picture, and the question is, what is the shape of the red object? And how the neuro-symbolic principle would solve this problem is, obviously, it would parse the scene by looking at the objects individually and their properties. So it would find out both objects and the properties. Then the semantic parsing, which would be a part of the same model, would actually figure out what are the concepts and what are the parameters of this picture, and it would come up with a set of operations that need to be applied in order to answer this question. And then, when these 2 are combined together, the result would be that, yes, I'm filtering the table for a color red. This returns row number 2. And then I query for shape, and for the name shape, and then I get the value, which is sphere. And this is how I resolve the problem. So how is this better compared to the previous model and maybe using neural networks and writing some code and so on? Huge advantage of this approach is that we reach extremely high accuracy levels, and in the cited papers that you will see that are all accompanied by data sets and some Python code and so on, and I will provide the links later. You will be able to see that the VQA algorithm, Neuro-Symbolic algorithm, is extremely accurate, almost 100% accurate in answering this type of more complex questions. The second advantage, and this is a huge advantage, is that this level of accuracy is obtained with just a fraction of the test data samples compared to all the other algorithms listed here. So if you look at the other algorithms, obviously the blue one on the top is the one from MIT IBM lab. You will see that it reaches very high levels of accuracy, even with a very small number of training questions, while all the other algorithms are, I will say, pretty inaccurate until they reach a humongous number of questions, like 700,000. So basically, in this case, with only 10% of the questions, or even as little as 1% of the training questions, you reach immediately very high levels of accuracy. And the advantage number three, and remember what I said in my earlier presentation about how do we go towards the general AI, and this is transparency and interpretability. Sorry. So since this algorithm is also generating a kind of a program, a set of operations, we can always go back and see how exactly this model came to the conclusion, and we can, let's say, quote unquote, debug it and fix it if there are some errors that we find in this example. So this is the future of the research. So what I've shown you is this first line on the top, that is the work from 2018, which is the VQA algorithm. Then what comes next is the concept learner, and then the meta concept learner. The concept learner, in the first example that I've shown, we have kind of hard-coded the properties and the values. In the concept learner, the properties are still predefined, but the system can learn new values or train itself on the new values by itself. Then on the meta concept learner, it can autonomously learn completely new concepts, so find new properties. And then obviously the research is going toward examining images, real life images and videos. So not to go into details, but concept learner means that it can find out by itself that red is another color, and then it is able to answer the questions that contain red. Then when it comes to meta concept learning, it is able not only to find the, let's say, relationships which are given in the questions, but then it is able to answer the questions like, is red a same kind of concept as green, or is cube a synonym of block? So we're basically adding synonyms, and in this way highly enriching the number of questions, number of ways in which you can ask a question so that it can be answered correctly. And then I will not go through this whole program around how does meta concept algorithm work, but bottom line is that it is discovering the new concepts and the new properties and their values as it is learning from the training set. When we go toward generalization, then basically we can train the model that there is an airplane in the picture, and then by asking a question, is there any plane, it is able to register that this is a synonym, and it's able to answer the question automatically, even if we did not say in the first picture that this is a plane, and similar for the kid and child, and so on and so on. So after this, hopefully some of you may decide that they want to have a look at this and maybe play with these algorithms to see whether they are applicable to some of your problems. And my advice is to start with a data set and the research paper called Cleverer. And this is collision events for video representation reasoning. So this is basically a set of training videos where these cubes and balls are colliding with each other. And there's a data set, and there is a code that is able to cover the following scenarios, the following questions. You can, answer questions like, how many spheres are moving in this video? What shape is the second object to collide with the gray object? Or the explanatory ones, which of the following is responsible for the collision between the gray object and the cube? And then you have several answers offered, and then the AI model will come up with the right answers. Or predictive model, what will happen next, what will collide with what. The counterfactual, what would happen if then analysis, basically. So you can already see that it is extremely powerful concept, where it is looking at right now these are rendered pre-configured videos, but in the future and already some work is happening with that, it will look at the real life videos and be able to explain what's going on, what will happen, or what could happen if some of the parameters were changing. So looking ahead, some of the examples of your questions that you could answer with such kind of systems is, how many crashes would happen in this intersection if we change the traffic light models or timings or signage, or, why is factory A producing more than factory B, or in the end, why is our database down, And in the end, I provided some slides which are providing some other models or ways, let's say, paths of research in this lab. One of them is quite interesting. This is learning that is trying to imitate the way babies or humans learn. So in this way, AI model is looking at the picture, and from the picture, it is trying to find out all the possible outcomes and all the possible actions and the order of actions and the conditions which lead to certain results. So in this case, it would say, yes, the baby can pick up a cube, but it can only pick up a cube if the hand is empty, and it can only pick up the cube from the top, and so on and so on. This is all figured out from the picture itself. Then, a slightly more complex model where symbolic planning is used. So this is a combination of, this decision tree that applies to, chess or Go or this puzzle game, and the image recognition. So basically, there is a algorithm that looks at the current state of the puzzle, and combining that with the decision tree that comes from the symbolic AI world, it is able to quickly predict what is the next step, or how to finish the puzzle, or how to solve the puzzle. There is also a kind of topic of verifiably safe reinforcement learning, and this is something that thinks about, how do we make sure that all the inputs that AI model is getting are safe. If you take like self-driving car, for example, obviously when a driver is driving and it's teaching the AI model, driver is making some mistakes or some bad decisions, and even those mistakes and bad decisions are going into the training set of the model. And then this whole research, let's say, project is working around how do we define what is safe to come into the model, and what do we need to take out of the training set for the model. And then one more fun kind of research topic is the causal inference. And this is kind of scientific approach that is trying to figure out why are some metrics, some two curves similar. And one of the kind of good examples here is that they discovered that the curve for the divorce rate in the state of Maine is almost identical to the consumption of margarine in the same area. And obviously, at first glance, these two things are completely unrelated. However, the kind of the task of this research is to figure out, is there maybe some way in which these two are related, and how do we figure out these features that are maybe connecting these two curves? And there's another funny example that says, is caviar a risk factor for being a millionaire? So these kind of figuring out what is the cause and what is the consequence type of problems are quite interesting, because in complex systems this is very difficult to do manually, and you need AI to do things like that. There are lots of other types of research that you can find on the portal of the MIT IBM lab. But what I want to conclude with is that obviously, based on the results of this research, symbolic AI is a good augmentation of the neural networks, and symbolic AI is here to stay, or neuro-symbolic AI. Together, they can produce much better results with much less training data for some classes of problems, and this is extremely important. And this is something that I want you to take away as a part of this. And remember that all of these examples, like What's on Jeopardy, game show AI, or project debater, which debates on some topics, or indeed these machines that are playing Go or poker and beating human champions, they are all based on this combination of these two, let's say, mathematical approaches. So that's it from my side. Sorry about running over time a little bit, so I'm opening for questions.
Yeah, unfortunately, we won't have time for questions, as the other keynote talk has already started.
Okay, sure. yeah. So okay.
But I just want to say it's a very fascinating topic, and it's a very promising topic as well. So thank you for presenting it at the conference. I hope you enjoyed the experience, both today and the previous days as well.
Yeah, thanks very much. If you need more information, just reach out to DSC team. They know how to find me. So thanks a lot for your attention, and sorry about going over time.
It is completely okay. Thank you once again, and hopefully see you next year. Thank you.
Yeah, of course. Cheers. Bye bye.